Fortunately, hasn't come that far today. He's just come up from Southampton University. This is Gintautas from the LituanicaSAT-1 team, also known to us as LO-78. I think the latest I read was it was 230 kilometers or so and falling, but no time for the black armbands yet. It's still going to be up there for another week or so, and I look forward to hearing about the satellite and the team during this presentation. Thank you very much.
All right. Screen mode. That worked. Okay. So we named our satellite by the name of the airplane that was flown from US to Lithuania with a single fuel tank on 1933. But unfortunately, it crashed. But it was lucky for our satellite. Well, it's going to crash eventually, but well, it worked and fulfilled all of our expectations. So first of all, I would like to thank all radio amateur community, and a special thanks to Mike Ruprecht. So for all the support and enthusiasm, and well, yeah, actually all the data and all your submitted telemetry readings were really helpful in debugging our satellite and just gathering all the statistics. So first of all, every member of our team had, well, probably more or less different expectations and reasons to participate in the project. But I guess the key unifying factor was the idea that we wanted to launch the first Lithuanian satellite and to take the first photo from space. It wasn't something scientific; it was just an idea. So we were very enthusiastic about it. So along with that, we also wanted to stimulate the collaboration between the universities, well, somehow, and within the university, just to, well, I don't know, just to stimulate the interest. And also we wanted to raise the interest of the general public, so especially the younger generation, to be aware of such technologies and that they can be fun. And also we wanted to try to create a platform for future projects like Lituanica, and hopefully even create new opportunities for business and education. Yeah. So the mission, from my perspective, the mission has started in July 2012 when I saw an article in a local newspaper about two space enthusiasts who were planning to create a first Lithuanian nano satellite. So I was really interested into that. So I dropped them an email, and well, from the conversation we kind of understood that we're gonna get along very well. So it took us roughly 6 months to assemble the core team, roughly around 7 members. We are all volunteers, and actually it was our secondary or even third activities. So we worked in the evenings and during weekends. So it wasn't our first-class citizen in our life. Well, at least not realistically. So we started with the hardware development, and unfortunately, in the middle of the development process, a new competitor arose. So basically, our team suddenly split, and that split part of the team created a new project called LitSat, confusingly, and they declared that they're going to create their own first Lithuanian nano satellite. Well, we took an optimistic approach on that, and we thought about, well, competition is always healthy, so why not? So so we continued with the software development and, well, did some testing. So basically the whole development took us slightly more than 1 year, and after that we sent off the satellite to NASA, and there was several months of nervous wait and regrets what could have been done better or tested Yes. So, and finally, in the end of February, our satellite was ejected from International Space Station. So the first month was quite nervous because, well, thanks to Mike, we immediately received the confirmation that our satellite works. But unfortunately, for the first month, something was wrong with the communication, and we had constant brownouts and even, I think, blackouts in the satellite. So that's something to do with the undeployed antennas, I guess, and poorly configured initial settings in that software. Yeah, but finally we got it under control, and it's expected to re-enter the atmosphere next week. So it shouldn't last until the end of next week. Yeah, but it's still orbiting. Yeah. All right. So probably this presentation will be slightly more technical, but I'm not going to cover the hardware part because I don't have competence in that, well, apart from breaking it. So yeah, so we focused, that's our satellite scheme, and we focused on the ARM module. That was our onboard computer that directly communicated with the ground station and controlled the satellite. So we also had and the rest, we treated the rest of the components as peripherals. So we had the Arduino module, electrical power system, and FM repeater. So as you can see, FM repeater is not connected to the rest because it was kind of an independent module. We operated it just by switching on and off the power supply, and that's it. It didn't have any configuration. And we used I2C bus mainly for watchdogging purposes and communicating with EPS, and we used mainly UART to communicate with the rest of the modules. So firstly, our module. So that's one side of our made PCB. So we used ARM M4 Cortex CPU. We downclocked it to 92 megahertz just to conserve power, and we had gyroscopes, accelerometers, and magnetometers, well, just standard equipment on board, and we planned to use SD card for telemetry data storage, and also this ARM module watchdogged the link with the ground station. So basically, if we don't establish a communication with the satellite, it just reboots the whole system within like 24 hours. All right. That's our transceiver, Helium 100. So probably techie guys will like this information. But what we needed is a support of AX25 protocol, and it had a full duplex feature, but we didn't use that because, well, the communication is not so intense in our case. Actually, one comment about this. Well, we really liked this device, but but the documentation was, well, as for a device that costs $5,000, this is like on the documentation there were some fragments like writers' comments like, okay, in the next draft revision we should improve this section. So it's kind of, I don't know, for $5,000 we expected slightly more verbose documentation. So anyway, so that's the other side of our PCB. That's Atmega CPU, 888, 8-bit, 8 MHz, 8 RAM, and it controlled beacon. It's connected here. It controlled the beacon, camera, and SD card, where we stored the camera, and also it watchdogged ARM. So basically, we were very sensitive about our satellite not hanging up. So we had set up lots of watchdogs. So we used BeeLine radio beacon, and we connected it separately, so it was to the power supply. So just to make sure that if something goes wrong, at least we will have a beacon transmitting some telemetry, so we could at least figure out or try to figure out what's wrong with the satellite. That was part of our minimal success criteria, which was almost guaranteed. So we used quite a simple VGA camera. It's like VGA resolution. It automatically produced JPEG pictures. It was half automatic in the sense that the exposure was automatic, but we just mounted on a fisheye lens with the infinity focus, and that's pretty much it. So that's proud selfie of the satellite in front of the mirror, which we got from the security office. So we just went them, took them by surprise, and asked for a mirror. So yeah. As for electrical power system, we used GomSpace Nano Power product. We're really satisfied with this product. Probably key features are 3.3 volt and 3.5 volt fully controllable channels, and also it comes with some predefined default non-configurable power modes like blackout and brownout, and some configurable like safe and nominal modes. So basically, depending on the voltage, it adjusts which channel should be switched on or off. And also it provides a number of watchdogging features, but we used one of them. It's like we set up watchdog on I2C bus, so in case something goes wrong with the satellite and other modules do not respond, we can reboot the whole system. So we use the Lithuanian-made solar cells. These are silicon-based, custom-built for our satellite, and they're generally low-cost solution. And currently, judging from our telemetry data, they are still in a good condition. We had some, as I mentioned before, we had some brownouts in our satellite, but probably that's not because of the faulty solar cells, but probably because we've miscalculated our power budget. Well, we're not certain about that. All right, so probably the most exciting experiment aboard our satellite, and quite unexpectedly exciting. So it's a FM repeater. So as I understand, it uses FM modulation, and yeah, it uses radio amateur frequencies. And currently, there are only 2 more of such kind of devices in orbit. One is in Saudi SO-50 satellite, which is full-time operational, and one is aboard International Space Station, as far as I know, which sometimes gets activated manually. So the general feedback about this FM repeater is really good. We're very satisfied about its quality and its power efficiency. And one of the significant advantages of using such type of FM repeaters is that it doesn't require sophisticated equipment in order to use it. So basically, you can use a simple handheld radio, at least I was told, and one of those simpler antennas. And yeah, one of the creators' opinions about this FM repeater was that actually it should go as a default option for nano satellites, because it's really energy efficient and has a very good quality, communication quality. Well, that's a prototype of the FM repeater. Well, I don't know. It immediately reminded me Einstein's haircut, but so I think it's in a heat camera here, being tested for heat resistance. All right, so proceeding with the functional part. So we focused on key system requirements like fault tolerance. So we assumed that our satellite is expected to, well, we expect it to crash at any time and anywhere inside the satellite, and we expect to handle these faults. So basically, that's a key principle in designing safety-critical systems. Well, this is kind of a safety-critical system. Also, we wanted to implement a redundant component control, leveraging EPS feature to control hardware power channels. So we've implemented this like this. So basically, in our satellite, we can control most of the components by hardware, just by sending commands to the EPS unit, just to switch everything on or off. And a soft mode, we've implemented that in a software. So basically, in case something goes wrong with the software, we can always switch back to the hardware. And since we've dealt with the fault tolerance, it doesn't really matter if we abruptly switch off the channel, because the system handles that. So, so we have some redundancy in control. fine-grained and more rough. So also, well, we wanted to make sure that we have a watchdog, and in case of some deadlocks, well, we can reboot our system. Also, some of our operations were really heavy on power consumption, so we couldn't allow them to run at the same time. So for that, we've defined a few software power modes, operational modes, in which only specific operations could have been performed. And also, we needed a lightweight network protocol to transfer packets and data packets and commands, because we didn't expect a really good communication quality. So regarding the requirement specification, since I'm studying PhD in the University of Southampton, I thought, well, maybe I could make use of my subject and, well, try to use some of my knowledge. So I wanted to make an experiment, and I'm working with formal methods, formal systems. So basically, what does that mean? Formal methods are formalisms, mathematical techniques, how one can express plain English requirements into a mathematical model, prove that its consistency, and then, according to the feedback from the formal strict model, you can refer back to the plain English requirements and correct them accordingly. So I wanted to leverage that that knowledge, and yeah, so basically the process looked like this. Firstly, we defined the requirement specification in natural language. Then I tried to translate part of it because to the mathematical model. Basically, I'll show you how the stepwise refinement looks like, and yeah. So in case there's some inconsistency in the model, I try to correct it, and then having that feedback, I go back to the requirements and correct the requirements. So firstly, before the development, we wanted to make sure that that our requirements are correct. So I actually barely scratched the surface, so I couldn't publish that because, well, really, it's very time-consuming and slow process. But still. So I'm quite satisfied with the results, because we still found some inconsistency. So, for example, the abstract layer of my mathematical model, just an example, but it looks like this. We have a system which is on only after the ISS launch. So we put another layer on top of this abstract model and introduce the first refinement. So basically, we expand this on state. And we add two substates of the satellite, EPS control and ground station control. What does that mean? That means that in EPS control, when the power goes down below some certain threshold, we no longer can control a satellite because the channels are switched off and the satellite is in a critical state. So this state is basically for informational purposes. And this is ground station control. This is where a satellite is actually operational. So in the next refinement, we elaborate these states. So we have brownout and blackout states here. And in the ground station, now we've defined software. These are more or less hardware states, brownout and blackout. And these are software defined in our ARM module, a low voltage and nominal voltage modes. So basically depending on the voltage, we switch between those two. So if we elaborate ground station control more, we have in the lower voltage, we have idle mode, where we do not perform any operations. This is kind of a semi-critical state where we conserve power. In the nominal mode, we have a default nominal mode, where only standard operations like housekeeping, telemetry data gathering run. And we have added a science mode, where we have data modes and FM repeater mode. So basically, these are really communication and power-hungry modes, so they're mutually exclusive, all three of these. So the purpose of this modeling was to make sure that these operation modes, energy modes, low voltage and nominal voltage, and the actual operations are consistent and do not interfere and occur exactly at the time and only within bounds pre-designed. So with my mathematical model, I've kind of made sure that requirements are really consistent, and we have the right operations occurring at the right moment. So for the implementation decisions, for the satellite, we used a good old C. Unfortunately, we used Kale RTX operating system, which is a commercial product. It's not a free RTOS. That's really unfortunate, but due to critical lack of resources, especially human resources, we had to stick with this commercial version. So we had sponsors that sponsored us with this version, and we had people from the same sponsor who were familiar with this operating systems. So we thought that we're not going to take any chances and stick to this. And also, it was perfectly optimized for ARM CPUs. So we, at the same time, we solved power consumption problems. For ATML, we used just standard Arduino package, its libraries and editors. For ground station, I'm not sure if there's a specific reason, but we used Erlang programming language. It's a functional programming language and really powerful and really fault tolerant, but well, I'm not going to expand on this. And for communication, we've developed lightweight UDP-like network protocol ourselves. So a rough ARM software architecture looks like this. So basically, that's the most complex software that we have on board. So maybe this will be useful and give you some ideas. So basically, we've defined a library stack, just common functions like, I don't know, this is typical. Then we've defined always created, never destroyed tasks, background operation tasks like telemetry, housekeeping, power manager tasks. They can only be stopped and run again, but they're never destroyed. So basically, we've tried to avoid memo locations and all these things as much as possible, and rather to occupy the memory. And one of the background operations was scheduler. So basically, our command handling was done by scheduler. So it received up to 10 commands at a time. So and when the delay from the command expires, scheduler creates a runner task, and runner actually runs our operation. And if the power modes and operation modes are fine and they are consistent with the command, we just continue with the command and then destroy the runner task. Otherwise, we just discard the command and tell the scheduler that it's got one more space on the stack. So regarding our success criteria, luckily, with the limited testing, we managed to reach all our success criteria. It's like in the minimal, we just wanted to get it launched at all and just assemble the satellite. So the second point was to deploy the antennae, and I think I suspect we had some initial problems in the initial 2 weeks, but they got solved after a number of times trying to deploy the antennas. We finally succeeded. Also, we wanted to receive a radio beacon, and thanks again to Mike just for being really active and yeah, getting that signal immediately after the satellite got launched. And the nominal success criteria, we had the satellite and ground station communication and testing FM repeater. So we were very, very glad with FM repeater. And the maximum success criteria, we had satellite stabilization, which I think it's quite evident that, well, it finally got stabilized. We received telemetry data and took a photo, so we're very happy of that. So that was one of the idea points. One misfortune. Telemetry archiving to SD card does not work. That's mainly because it's been never tested. We didn't have enough time for that, so we were desperately behind the schedule, and we didn't have resources working on weekends and at nights. Well, it's like a pleasant surprise. We got an Oscar number designation, so we're very grateful for all the radio amateurs for that. I guess you all know way better what does that mean, and how great is this award is. So that's the first photo. So that's obvious proof that the Earth is flat, finally. And we were fed lies all the time, so yeah, finally we got that proof. So, so actually, yeah, we can see some antennas here, some flare from the sun, and Earth. Since it's a fisheye, so, well, there is some huge distortions. But anyway, we're very happy with this photo, even though it's simple, but it's the first photo, and it's like, well, finally we achieved that after like. And lessons learned. So operators struggled to use the satellite. So actually, it was quite confusing because we had overlapping power modes. Like safe mode was available in both, in the EPS system and in our satellite. So basically, it was really confusing. And I think due to lack of time, we had quite a poor documentation or just a reluctance to read it. Well, that's quite a common thing actually to do. So it's quite debatable here. Probably with a pint of beer, well, we can discuss this. So, and one of the principles, do it quickly and make it right later. It never works, and please do not try that, because whatever you do, it's going to stay there till the end of the project. So always do it right. And all timers must be configurable, because some of our watchdog timeouts were hard-coded, and actually that was quite a big part of our misfortune in the first month, because we couldn't reconfigure it, and since the antennas were not deployed successfully, the watchdog just kept timeout and reset everything to a standard configuration, and then the standard configuration, which we have miscalculated, used to discharge our batteries. So basically it was kind of a closed loop, and we were not sure whether we can come out of that loop. And use homogeneous environments for reusability. So, for instance, only ARMs, because now we had ARM system and Arduino system, and well, basically it was like a redundant labor, so we didn't like that at all. So, and reflash option. So this is a really handy feature. So I think you should have this. So thank you very much.
Well, I think congratulations to the entire team, Gintautas. You have managed to put a project together within a year, see it launched, okay, after that, but I know a lot of people have been struggling to do that, and I think you should be very proud of what you've managed to achieve. I think we'll just have a couple of questions from the floor, if we may, because this is a very exciting project, and I'm sure there will be a few things that people have to ask based on the presentation today. Any questions? I'll just head back to Drew, if I may.
I just wanted to thank you for including the FM repeater on the CubeSat. It worked wonderfully, and it's, I think, the essence of where we're headed. I'd like to see all the CubeSats do something like that. It worked very well. A quick question. Do you plan on, or have you published anything about the repeater? I noticed it's nice, compact, looks like one card.
Not yet, but that's a great idea, and I will definitely forward it to its creators, to Žilvinas, Batista, and Žilvinas at Kučiūnas. Yeah, I'll definitely let them know. But I think they're very enthusiastic, and I think they would definitely use this advice.
Okay, and a question which I can almost predict from the front.
No, you can't, because what I want to ask you is it was about the SD card. Right, you said you didn't test it before the time. Do you have any speculation of whether it was the system or whether it was the SD card itself? We're planning a satellite also using an SD card, and there's been a lot of talk about SD cards don't operate in space, but we can't find any real evidence for that.
Well, in our case, that was my mistake, and that was software mistake. Yeah. So yeah, but basically too many precautions and too many safety features that actually just killed the functionality. Yeah, but well, I didn't have enough time to test it. In general, our thoughts about SD cards. I would consider them being quite reliable, but you should focus not for an ordinary like corner shop SD card, but for some more sophisticated industrial grade SD card that has error corrections on board on the hardware. And definitely you have to design your system in such a way that it wouldn't depend on the SD card. In case it fails, the system shouldn't even notice that. I mean, the system should take care of it. So definitely consider failures.
Okay, thank you very much. I think we'll have to stop there because we are about 4 minutes over. We might be able to get a personalised response to the question on the internet in a while after this session. Okay, well, thank you very much indeed.
Thank you.
We'll invite our next speaker to the front. If we could have the radio mic, that would be